Hello everyone, I am welcoming you all once again to this channel. Today I am going to make a video on our Gaussian software where we will see how to calculate the energy of an excited state. So here, what is an excited state? So typically any system always wants to present in its ground state where it can minimizes its energy. But if we are adding some extra energy, like it can be a light energy, it can be heat energy, then the electrons of that system may rearrange themselves and they might go to some excited state. So they are this like the charge of the system will remain the same, but the multiplicity may differ depending on which level the electrons are arranged or like that. So for that we can use this excited energy state calculation, for which we need to only play with the multiplicity of the system where like based on the electronic arrangement. So here I have some input files, so I am going to show it here. So one I have in the singlet state and one I have in the triplet. So I am opening now the singlet input file. So here you see that we have taken one structure where we are optimizing that structure, like optimizing with the frequency calculation with itself, and we are using this Gaussian 6311 plus GDP basis set, and then this population is full geometry connectivity, and here we have used the DFT label as AMO62X. And now here you can see that this is nothing but the charge here is given as 0 and the multiplicity here is 1, that is the singlet one. And if I will open that triplet state, then here the only changes over here is that this is same charge state, but the multiplicity here is 3, that means it is the triplet state. And here also sometimes while calculating this excited energy state, like when we are going ahead from singlet to triplet, then some kind of issues we also face. So to minimize those issues or to like we can prevent those Gaussian errors by having this particular input, that is this SCF is equal to XQC, and the maximum cycle here also you can write as 512 or any number you want you can write. So otherwise before converging it might give some error, so that's why we have taken this one. So now I will be opening both of these files in our GauView software. So here I am opening my GauView, and the singlet GJF and also the triplet one also I will be opening here. So you can see that this is the singlet one, both the structures are same. And here if I will go to the calculation part, you see that we have chosen OPT frequency and the method over here is 6311G, and whatever the method like this M062X is not a method that has been provided by this GauView, but if you want some additional keywords we can write it over here. So that's how we have written here. Next is here this charge is 0 and this state is singlet state. Okay. And for this one we have taken similar structure, and here also this OPT frequency we are calculating, then the method is same, only here instead of charge we have taken triplet. And here also some additional keywords, whatever we have written, this SCF equal to XQC and maximum cycle of this much, everything we have written over here. And now if you can run these input files and you can find your output. Now I am going to close this, and I will be opening the output file separately. So singlet log and triplet log I am opening both. So here we can see that this is our singlet log where we have like optimized the ground state for this molecule, And here you can see that in the result we have conversed with all these numbers, and here in the thermochemistry also, as we have performed this OPT and frequency here, so we are also getting the thermochemistry part over here, and it is showing the imaginary frequency for 0. That means this is the ground state. Okay, next is here I'm opening for the triplet state. You see that this is also conversed, and here also all the thermochemistry part has been given, and here you see that the imaginary frequency for this one is 1. That means this is not a ground state, it is like this is a kind of transition state or any kind of state, like, but not the ground state, because we are getting the imaginary frequency as 1. And here also you see that like from here to here, when we increase the multiplicity, that means we rearrange the electronic position, then the bond breaking has been occurred. Here you see that here 1, 2 and 3 bonds has been broken. And also if you want, I think we can also do that, if you want to modify this bond also, we can simply click and we can go to builder, and here the modify bond, there is an option. So here you can add bonds between whatever atom you want, and here then here you can add. So okay, so this okay, yes, you see that now we have added some bonds, but this and this atom are too far. If I'm clicking over here, you see that what is, okay, let me come to, yeah, now you can click over here. You see that the bond distance between this and this is 3.86089, and here also we have added another bond. Here the bond distance 2.19, and here we have added another, and here the bond distance 2.15. That means this is okay, but this and this atoms are very far from each other. So this way you can modify little bit using the GauView for the visualization purpose. And this is how one can perform some excited state calculation for any kind of reaction mechanism, like how this state is from this state to this state, a system can go ahead. So this thing we can see from this way. And also here another thing I would like to show. Here we can see that the charge distribution over here. So I am showing the number. You see that here the charge is, overall charge is 0, and here also the overall charge is 0. Rather, you will see that during the process, some of these atoms, they have gained some fractional charges. You see that like overall system is charge neutral, as we have given the charge as 0, but you see that during this bond breaking and this thing, when they went to excited state, so some kind of charge interaction they have filled, and that's why this kind of fractional charges are coming. So this is how you can analyze your things using the excited state energy and the ground state energy calculation. And this much for today's session, and thank you all, and bye bye.